Okay, so let's continue from yesterday. What we have covered so far is that I defined linear classical LDPC codes for you, and I showed you constructions for good expander classical codes, both random and explicit. And I mean, what's nice is that even at the classical level, these models are already interesting as new types of fun StatMech models. Again, we're having a lot of fun playing around with these models from a more physicsy perspective. Okay, and then I gave you a very baby's introduction to homology theory and gave a description of all quantum CSS codes in terms of homology theory, right? And in particular, what we showed is that at the basic level, to even define a quantum LDPC code needs a level 2 or a 2-dimensional chain complex. So what's the plan for today? Today, I want to describe gauging in terms of these boundary maps that we've been talking about. And the focus will be on the properties of the classical code that will be gauged. Okay, like what properties does the classical code need to have in order to get something non-trivial happening in the corresponding gauged quantum code? So that's going to be the perspective that I'm going to be taking there. And with that perspective, I then want to describe various of these product constructions that have appeared in the computer science literature in more physicsy terms. Okay, the goal of those product constructions will be to enrich models, take simpler models and enrich them with properties that you need in order to get interesting quantum codes at the end of it. Okay, so the simplest thing that you want to do out of these product constructions is to build these higher level or 2-dimensional chain complexes starting from 1-dimensional ones. Okay, so this can be this sentence can be reinterpreted as a way to build quantum codes from taking products of classical ones. Okay, so that's the simplest thing you want a product construction to do, but then these can also be enhanced to enrich codes with different other features that might be, again, interesting to a physicist, even if they don't do much for computer scientists. Okay. So just to, again, tell you for the third time what these boundary maps are. Okay, so we have in mind a vector space V0 defined by the bits. We have n bits. So this is an n-dimensional vector space. It lives in F2 to the n. There's a basis vector for every bit. So every vector in this configuration space or in this vector space, this is some length n vector of zeros and ones. And what this length n vector does is it just picks out for you some subset of bits. Okay, it tells you everywhere there was a 1, that's a bit that's in your subset of bits. Okay, and likewise, once you have a basis set of checks, those, if you have m checks, those also define an m-dimensional vector space, which we're going to call V1. This is F2 to the m, and likewise, there's again a basis vector for each check that you're going to, each of these m checks. And if you have a vector in this vector space V1, this is now an m-dimensional vector of zeros and ones. And once again, this picks out for you which checks are part of your subset. Okay. Now this map, okay, this map delta 1, which takes me from checks to bits, this is actually the transpose of this parity check matrix that we talked about. But what this map is doing is it acts on this m-dimensional vector space because it's taking me from checks and produces a vector in an n-dimensional vector space. And the way you should think about it is if you feed in a vector representing some subset of checks into this map, what you get back is the subset of bits that are in the support of the checks. Okay? And of course, naturally, given that we have this map, this is just a matrix of zeros and ones of size. This matrix has size m by n. There's correspondingly a transpose matrix, okay, a transpose map, which maps me from bits to checks. And if you feed in a subset of bits here, what this map returns, this transpose map returns, this is the subset of the checks that are triggered by the bits, okay? So you can think of this as the syndrome. This transpose map is returning the syndrome. If I feed it some configurations, you know the all zero state is always a code word. So now if you feed it something different and you get back a vector with some number of ones triggered in there, then you know that those are the checks that got violated by that collection of bits, okay? So pictorially, for the 1D Ising model, okay, I have my 1D Ising model. This is supposed to be periodic boundary conditions. My bits, again, in the language that we learned yesterday, this 1D Ising model is just a cellulation. Okay, you have bits and edges. You can view that as a cellulation of the 1D circle. You're going to put bits on sites, which are 0 cells, and checks on edges, which are 1 cells. So now if I take a subset, which is just picking out that one check there, and I ask which bits are in that subset, okay, that's what this boundary map delta 1 tells me, and you know that it's those 2 bits, okay? If I pick some other collection of subsets, this map acts linearly, and it's all modulo 2. So from that particular check, I have these 2 bits that get triggered, and then from these 2 checks together, I have those 2 bits that get triggered and not the one in the middle, because the one in the middle gets triggered twice, and mod 2, it doesn't flare up, okay? And now, notice that with periodic boundary conditions, if I actually take all the checks in this set and look at their boundary, then you find that nothing is triggered here, right? Because with periodic boundary conditions, you know that the product of all the checks around a ring is just going to be the identity, so no checks get triggered. So what that means is this gives us a way to define redundancies among checks. Redundancies among checks are linear dependencies in the check space. They're a collection of checks which don't act on any bit. So if you have this map delta 1 and you look at the kernel of that map, the kernel of the map is telling you what are subsets of checks which don't trigger any bits, right? So the kernel of this map defines a basis for the vector space of redundancies. Every kind of object that we're going to be dealing with can have its own vector space. Okay, we have a vector space of logicals, we have a vector space of bits, we have a vector space of checks, and now this kernel of delta 1 will define a basis for the vector space of redundancies. Okay, now let's look at the transpose map. Okay, so if you had an all 0 state and you flipped a bit on that site, you're now asking which checks get triggered because of that flipped bit. And you see that these 2 checks here get triggered. If you now flip 2 bits next to it, okay, then again with modulo 2, you flip this bit, you created 2 domain walls. Okay, those are the locations of your triggered checks. And then your domain walls hop as you flip more bits. And by the time you're done flipping all the bits, then you're back to the code space and no checks get triggered. Okay, so in this language, a symmetry is a collection of flipped bits which do not trigger any checks. Okay, so the kernel of this map, delta 1 transpose, now defines a basis for the vector space of symmetries. Okay, and this is, of course, also a basis for the vector space of logicals, because we talked about how symmetries in this classical code are exactly the logicals. Okay, these are these configurations which this is in the code space because no checks are triggered by this configuration. And any set of bits that you need to flip to get a configuration in the code space defines a symmetry of your Hamiltonian. Okay, so this is great, and this delta and delta transpose that I showed you should hopefully remind you of some of the things that you learned in Shohang's lectures, right? Because what you can see now is that what this transpose map is doing is it's just taking you from bits to checks and checks to bits. Okay, so this is nothing more than a Kramers-Wannier duality, right? So if I have this code here, this classical code C, which is my 1D Ising model, notice that I've just put some labels here. Okay, the checks live on these boxes labeled A, and the bits live on these sites labeled I. Okay, and now once again, I have my checks. Those are defined through this matrix delta, which tells me, if I pick up a label A, which bits does it act on. And then I have the symmetries and the redundancies, again, all defined through these maps. Now, the point is that if I look at this transpose map, in which the role of bits and checks is flipped, the way to think about this is that an excitation in the original code, right? An excitation is a check that was triggered. And that check which was triggered in the original code now becomes a degree of freedom in its own right in the transpose code once you swap the bits and the checks. So the transpose code is writing a new model defined in terms of the excitations of the previous model. Okay, and this is going to be important because this is exactly what you do when you talk about gauging some theory. You want to write a new theory in terms of the excitations of the original one. Okay, so here, so that's what these first two rows are doing. And now from our discussion of the maps, what's clear is that the role of this transpose operation is to swap the role of symmetries and redundancies. Okay, so something that used to be a symmetry in the original problem becomes a redundancy in the new problem, just again given that symmetries are defined through the kernel of delta 1 transpose and redundancies are defined through the kernel of delta 1. So if you're swapping these two, you're swapping the role of symmetries and redundancies. Okay, so now if I want to do a unitary transformation between a model defined by a code and its transpose, okay, then you learned about this again in Shu Heng's lectures. This unitary transformation has to map between spaces which have the same dimension, okay? So because of this role played by symmetries and redundancies, you can't, if you allow the symmetry sector, if I just give you an Ising model, it's you'd say, okay, in symmetry sector +1, here are all the configurations, and in symmetry sector -1, here are all the configurations, right? So that's the full Hilbert space. But actually, if the symmetry turns into a redundancy, okay, the redundancy, you don't have a choice to not enforce the redundancy. It's just a product of everything that's one. So that actually forces you to work within the symmetric subspace if you want to define this unitary transformation. Okay, so in terms of dimension counting, the dimension of the symmetric subspace of these sigma variables of the original code is 2 to the n minus k, okay? And the dimension of this other code written in terms of the bits is 2 to the m minus k. And one line of algebra, you can convince yourself that these two dimensions are equal to each other. So you can do a unitary transformation between these subspaces, okay? So the upshot is that the transpose map naturally tells you how to do Kramers-Wannier dualities, which writes a model in terms of which gives you a new model, the transpose model, in terms of the excitations of the original one, but with the caveat that all symmetries on both sides have to be enforced. Okay. So gauging is exactly this. You want to turn symmetry defects, for example, the domain walls, into dynamical degrees of freedom, okay? So as we just discussed, you can use this transpose to get a new model with the bits and checks swapped, and this new model precisely promotes the excitations of the original model into the dynamical degrees of freedom. You're keeping track of, is a domain wall triggered or not? And now, again, as I said, this Kramers-Wannier duality maps between the symmetric subspaces of H and H transpose. So the last step that's remaining to get a full gauge theory in terms of these gauge degrees of freedom is to just remove this extra condition that we want to map between the symmetric subspace. Okay, so there's a systematic way to do this. You add in extra gauge degrees of freedom, and now you come up with and I'll show you how this is done in another few slides. But then you systematically add extra degrees of freedom, and you come up with a full gauge theory that can account for all the freedom that you want from these symmetry defects, and you want to kind of remove this constraint to get this unitary transformation. Okay. And the upshot is that for the 1D Ising model, I can go through this prescription, but we know that the Kramers-Wannier dual of the 1D Ising model is just the 1D Ising model. Okay, so we want to do this gauging prescription to hopefully get some non-trivial quantum theory out of it. But actually, for the 1D Ising model, you see that this does not give you a non-trivial gauge theory. Okay, you just get back the 1D Ising model with the role of J and H swapped if you were thinking of a transverse field 1D Ising model. Okay, so you need something extra in order to get a non-trivial gauge theory, and the extra thing that you need is you need your degrees of freedom, which are my domain walls, to be extended. You want the gauge theory to describe some theory of extended objects for it to be non-trivial. okay? And in the simplest case, like in the Ising model, these domain walls are just loop-like, but actually they could have much more complicated shapes. The point is you shouldn't be talking about a gauge theory in terms of point-like degrees of freedom. If that's what you have, then when you do the gauging, you tend to get back some kind of self-duality like in the 1D Ising model, okay? So we want to turn these symmetry defects into dynamical degrees of freedom, and you need these degrees of freedom to be extended to get a non-trivial gauge theory. Okay. So how do we get these extended degrees of freedom? We go back to the chain complex, okay? So again, you know, we left off last class by showing that if you want to think about the toric code or any CSS code, which is a quantum code, it's defined on a two-dimensional chain complex, okay? So there must be something else in that two-dimensional chain complex, which you can also think of in this language, okay, as a classical code that you can gauge, which lives in the same chain complex in order to get that quantum code, okay? So in the simplest case, to define a classical code, I just needed bits and checks, but that was just one map delta, right? And that just gave me this trivial kind of 1D Ising model example. So what I want to do is actually put in a classical code, but embed this into a chain complex which is bigger, okay? So if I put a classical code on this two-dimensional chain complex, so notice what that does now for the Ising model again. A two-dimensional chain complex in the simplest case that we talked about yesterday is just some kind of cellulation of a 2D manifold. So if that's my cellulation of a torus, then you know that there are vector spaces, again, associated with the vertices, edges, and plaquettes of this manifold. And you can go in to define a classical code. You just need two of these levels, okay? You need to put bits somewhere, and you need to put checks somewhere. That's all you need to define the classical code. For the quantum code, we needed bits, qubits, x checks, and z checks. So I needed 3 different vector spaces, and that's what these 3 different vector spaces are going to give me. But for a classical code, I only need 2, right? So I put my bits down in my vertices. I put my checks down in my edges. This is well and good. You know, that's what that picture looks like. Those are my bits. Those are my checks. But now the point is, because I have embedded this classical code in this higher chain complex, the point is that the existence of this level here gives me local redundancies in my classical code, okay? Because what this map tells me is that if I take an object in V2, which corresponds to some plaquette-like object, and I act on it with this map delta 2, that returns for me some collection of checks, and I know from the definition of a chain complex that that collection of checks, you know, so on this plaquette, it'll be those 4 checks around the plaquette. When I then ask which bits are triggered by that collection of checks, I should get that no bits are triggered, okay? So since the kernel of delta 1 is what's defining a basis for the vector space of redundancies, note that this B1, okay, this was this boundary chain that we talked about yesterday, this boundary 1 is the image of delta 2, okay, but that belongs to the kernel of delta 1, okay, because a boundary, by definition, the boundary of a boundary is 0, so a boundary is not going to trigger is not going to act on any bits for you, okay? So when you have this higher dimensional chain complex and you put your classical code on it, the existence of this level automatically defines for you local redundancies, okay? And I'm calling these local because everywhere in these lectures, when I write these maps, delta 1 and delta 2, I'm implicitly assuming, you know, at the algebraic level, your kernels for these maps can be completely dense, but because I'm going to want to associate these with codes, I'm always working with models in which these maps are sparse. And when I'm thinking about LDPC, and local here is just, you know, on a geometric lattice like that, it's literally local, but in general, it'll just be few body, okay? So that's that's what you get when you put in a classical code in this 2D chain complex. You get local redundancies. And by the way, you know, like this was 2D. You could talk about 3D, 4D, and so on, and keep building this structure up. But because of this composition of chain complex maps, if you had a third level here, that would just correspond to redundancies of redundancies, which are often called meta-redundancies, and you could keep going in that way, okay? So, okay, this is maybe beating a dead horse at this point, but just to do it, so now when I have a 2D Ising model with checks on the edges, I act with this boundary map. It tells me which bits are triggered. And now if I have 4 checks, okay, corresponding to the boundary of some plaquette object that exists on this manifold, then you see that no checks are triggered here. So this is again a redundancy, and now it's a local redundancy, okay, because you have this local plaquette there. And if I want to go in the opposite way, then you can ask if you flip one bit, which checks are triggered, and you actually get this star-like term, okay? And that star is going to become the star of the toric code. So that's not a coincidence. It's just telling if you flip this bit, then those 4 checks are triggered, okay? And if I flip all the bits, then nothing gets triggered, and that's just the Ising symmetry of the 2D Ising model, okay? So the point is that because this 2D Ising model has these local redundancies coming from this higher dimensional chain complex, the local redundancy imposes a local constraint on every configuration of domain walls. Since you know that the product of those 4 checks on that plaquette has to be +1, you know that you cannot have an odd number of domain walls leaving that plaquette. Okay, so we associate gauge theories with local constraints in your space, and you can see how this feature here automatically gives you this type of constraint that any domain wall that enters has to leave, so your domain walls have to form closed loops. Okay, and the fact that your domain walls form closed loops is, of course, extremely relevant for various properties that we take for granted in the 2D Ising model, especially in contrasting it with the 1D Ising model. And that's the fact that this is a thermally stable classical model. Okay, if you have you have a finite temperature ordered phase in the 2D Ising model, which is again coming from these loop-like excitations. And also that when you're going to gauge the 2D Ising model, we know that you get the toric code by gauging the 2D Ising model. You have a non-trivial Z2 gauge theory with a deconfined phase for Z2 gauge theory coupled with matter, and the toric code is 1 point in that phase. And that's coming, again, from the fact that it's these extended degrees of freedom that are going to become the dynamic 2 degrees of freedom in your gauge theory. Okay, so that's this perspective right here, that you have this 2D Ising model, which is, of course, a classical code. It's a 2D repetition code with these closed domain walls. And when you gauge it, you get a Z2 gauge theory, and the toric code is a quantum code, which is a solvable point in this Z2 gauge theory. And you can already directly see that these wave functions that we wrote for the toric code yesterday, which is in terms of this kind of loop soup. Okay, these wave functions are again directly being derived from these closed domain walls of the underlying Ising model that's being gauged. And we want to now think of this quite generally for any LDPC code. But the beauty of these maps is that even though I was using the Ising model as an example for everything I was saying, the structure was only caring about the maps that I talked about, the boundary maps. Okay, so this exact same prescription can be done for any LDPC code in any manifold or in any geometry defined by those boundary maps. Okay, so any questions before I keep going? All right. So now when I'm doing this so now let's go back and I want to do the full gauging. Okay, but the first step on route to gauging is this Kramers-Wannier duality. So when I'm doing the Kramers-Wannier duality, once again, I'm swapping a code with its transpose. So for the 2D Ising model, okay, you again have bits on the vertices and checks on the edges. And you know that you have one global symmetry for this Ising model. Okay, one global symmetry because you can flip all the bits, and that's your Ising symmetry. And as we discussed, you have many local redundancies. Now, when I do this transpose map, which swaps bits and checks, now you see that your degrees of freedom, okay, bits should just be viewed as like, what are the degrees of freedom that we're talking about? Your degrees of freedom now live on the links of this 2D Ising model, okay, because those are going to, again, pick up, is there a domain wall through that link or not? And then the checks are now these 4-body checks on the vertices, which look at the product of those four bits along that, on that star, okay? And it isn't a coincidence that this is exactly the X term for the toric code, okay? So the point is that, again, this transpose map is going to swap the role of symmetries and redundancies. So I had one global symmetry in the Ising model, that becomes one global redundancy in the toric code, okay? So this is the redundancy that we were talking about. If you multiply all these X checks, okay, you get the identity back. And crucially, the fact that you had many local redundancies means that you now have many local symmetries in the transpose code. Okay, so again, for a gauge theory, you want a model with many local symmetries, okay? And a different way to say this is, we were talking about the goal for a quantum code is to have an LDPC CX type of code and an LDPC CZ type of code. And all the checks in X and Z should commute with each other, right? So if you're only looking at the CX type of code, what you need is many, many local operators that are going to commute with that CX, and those local symmetries are going to define your CZ code. Or for those of you who like to think about one-form symmetries, it's these local symmetries that will make the one-form symmetries of this model deformable, because you can multiply with these local symmetries and get kind of homologically equivalent descriptions of the one-form symmetry that will be there in this model. Okay, so now if I actually do this duality, okay, and write the two Hamiltonians. On one side, I have the 2D transverse field Ising model. Okay, this is the model, again, the simplest model with the global Ising symmetry. And now I write the Kramers-Wannier model, and this J term, okay, ends up looking like something which lives in the links. It's just telling me is the link on or off, depending on whether or not there was a domain wall there. And this X term, which flipped one bit, now becomes a toric code star term, okay? But there's what's the missing feature again? Remember, like when you do this unitary transformation, then symmetries on both sides have to be enforced in order to get the Hilbert space dimensions to match up. That's the only reason we can call this a duality, okay? So when you do that, the fact that you had local redundancies here, which was enforcing your domain walls forming closed loops, on this side means that all your local symmetries now, so these are my domain walls forming a closed loop. And on this side, what that means is that any configuration of CZs, which is -1, has to come in this closed contractible loop, okay? So that means that all of these BP terms, which were the local symmetries of your AX, CX Hamiltonian in the toric code, all of those have to be enforced as +1. Okay, you're not allowing for any vortex excitations when you just do this Kramers-Wannier duality. But already you see that you get this non-trivial. You get something which looks very, very close to the full gauge theory, because you have your AX term and you've stuck it in a transverse field. Okay, so this is like a pure gauge theory already that you have. Okay, so if you want the full structure of, if you don't want to impose that there are no vortex excitations, if you want to allow for those, then you follow this standard minimal coupling prescription, where you start with your Ising interactions. Okay, so now this picture means that on every vertex I have my matter qubits, and on every, now I'm going to think in terms of a full quantum gauge theory, and on every edge I have a gauge qubit. And what you do is you take your interaction term, in this case this was the Ising interaction, and you minimally couple it to a gauge field. Okay, so every interaction gets coupled with this gauge field Zij. Once you've done that coupling, you want to allow for all local gauge invariant terms, because, so, okay, the first thing this does is it takes your global Ising symmetry, and now, because you've introduced these local gauge fields, you actually have promoted the global symmetry to a local symmetry, right? Because now what you can do is if you flip a bit on any given site or a qubit on any site, that's sigma ix, and you also flip all the gauge fields that are surrounding it, okay, then the theory is invariant under that. Okay, so there's a local Gauss law, which is basically telling you that you have the freedom to flip a bit as long as you a qubit as long as you flip all the gauge charges coming out of it, right? Good. So you can enforce this Gauss law because it's the symmetry of the Hamiltonian, and we can add in all local terms that are allowed by this local gauge symmetry. So what do those look like? This gauge symmetry is purely diagonal on the x basis, so I can just add in an x gauge field everywhere. That makes these background gauge fields dynamical. It allows them to fluctuate, okay? That lifts this constraint that you have no plaquette excitations. And then notice this BP, okay? I need the BP in order to have the toric code and in order to be in the deconfined phase of the Z2 gauge theory. But where is this BP coming from? It's coming exactly from the redundancy of the Ising model, okay? You know that every one of these link terms is gauge invariant by construction. We added in this gauge field to make this link term gauge invariant. But now I can take a local product of these terms, and notice that because your sigmas, your matter degrees of freedom, had a redundancy, by the time you're done taking this local product, all the sigma variables have canceled out, and you're just left with the plaquette BP term. Okay? So in general, if you have an interaction and you coupled it to a background gauge field, if you have local redundancies in your interaction, that's what gives you some local BP in your gauge theory. Okay? So this BP directly is inherited from that redundancy of the Ising model. So now when you put all those terms together, so this is my ZZ term with the coupling. I had an old transverse field. I added in a transverse field for my X, and I have this BP term. Once you put this all together, you get a full gauge theory for Z2 matter coupled to Z2 gauge fields. And this has the celebrated phase diagram from Fradkin and Schenker, where the different axes are basically, this is a pure gauge axis, and this is looking at fluctuations of these magnetic degrees of freedom. This is a pure matter axis that's looking at charge fluctuations, and there's a deconfined phase here. And the origin, you can, once you do a little bit of gauge fixing, you can convince yourself that the origin is exactly the toric code, okay? Which is a point in this deconfined phase, which is also the topologically ordered phase. Okay. So now this prescription, as I was saying, even though I was using the Ising model as a guide, it's a completely general prescription that works for any two-dimensional chain complex, okay? So now these vertices, edges, and plaquettes, they're in quotes because I'll show you examples in just a moment where they're not literally vertices, edges, and plaquettes, okay? The Ising model is nice because if I give you the cellulation of a manifold and I tell you that I'm going to put Ising checks on the edges, Ising checks are just two-body, and edges by definition are two-body, right? So when you do that, then the structure of what's there in your code exactly matches the structure of that underlying manifold. But in general, the edges are just checks. We saw already when we were looking at these graph examples, your checks can be multi-body, right? And your redundancies can involve more than 2 checks or more than 4 checks. So this is now going to be a very general structure where you just have some collection of objects here. This map delta 2 is going to define delta Z, okay? Because this is where I'm going to associate the Z checks with this vector space V2. I'm going to associate qubits for my quantum code with the vector space V1 on the edge degrees of freedom. I'm going to put vertices on these, I'm going to put X checks on the vertices. You have these maps. Delta 2 is just delta Z. It tells you how to go from something labeling a Z check to the collection of qubits that Z check acts on. And this other map, delta X, okay, has to take you from something labeling an X check to the edges that it acts on. But notice that this is the transpose now, okay, of this delta 1 map that we were talking about earlier. So the fact that you're talking about a chain complex means that the composition delta 1, delta 2 is 0. That's the definition. But this also implies that delta Z, delta X transpose is 0, or that HX and HZ commute with each other. Okay? So that's the definition of a quantum code comprised of my X and Z checks. But then, as we were saying, you can also put on the same chain complex this classical code, which has bits and checks and local redundancies. And this classical code is actually exactly CX transpose. Okay, we saw this for the Ising model. When I took the 2D Ising model and I looked at its transpose code, I got the X terms of the toric code. And now this chain complex, you can not only go in one direction, but you can actually also go in the opposite direction. And then you get this other condition for the transpose maps, which means that you can also put down a classical code on the dual lattice, where now the bits live on plaquettes, the checks again live on the edges, but now your local redundancies are on every site. Okay, so those are like, you know, if this was my condition, then there's a local redundancy on this site corresponding to multiplying those 4 checks around. Okay, so, and I can again gauge this, and the transpose of this is exactly CZ. Okay, so you have the Ising model and you have the dual Ising model, and these two are actually related by a classical Kramers-Wannier transformation. And then when you look at their transposes, they define for you the CX and the CZ of the quantum code that you're after. Okay, and again, this is totally general. Yeah.
So we want to make quantum code using the classical code. With the quantum code, if you think of a Hypergraph, we have checks and bits.
Mm-hmm.
But to make it quantum, we want to make these checks also as a bit by having a plaquette. But
exactly.
Is there a straightforward way to do for any generic code still satisfying good?
Yeah, good. Exactly. So that's the challenge. So the question has exactly hit upon, you know, what's the goal, right? So we talked about the standard code construction for good classical codes, and that had bits and checks, but it didn't have these local redundancies, right? It didn't have some notion of plaquettes. So the question was like, is there a general prescription to take those classical codes and convert it into something which has something like a plaquette, which would give me this 2D chain complex, while also maintaining goodness, right? And that's exactly the question, and that's exactly what these product constructions are trying to do. So that's what I'm going to now move on to. Okay. So okay. So I just want to emphasize this thing that I was just saying, that checks in general are hyper edges. Okay. We can write the code as a hypergraph, and the check can act on more than 2 bits. Okay. And likewise, redundancies are hyper plaquettes, which can involve more than 4 checks. So this geometry of a code, right? Once you have a collection of bits, checks, and vertices, this defines a kind of geometry for you, right? Because you know that you should think of your checks sort of as edges, and you should think of your plaquettes, your redundancies, sort of as plaquettes. Okay. So there's a geometry that's defined from the code, but in general, this can be distinct from the underlying some underlying lattice on which the code lives in the first place. Okay, and in condensed matter, we deeply appreciate the properties of physical lattices and their dimension. We know that there's this deep difference between the 1D Ising model and the 2D Ising model, but actually, you know, whoa, what happened? This code geometry is just as important in determining physical properties. Okay, in fact, I would say like this is really what's happening under the hood when we're talking about the difference between the 1D Ising model and the 2D Ising model. So let's look at a couple of examples, right? So what I spent all this time talking about is this DC is what I'm calling the dimension of the chain complex. So for the Ising model defined on any geometry, the geometry of the code and the geometry of the chain complex are the same. Okay, so this is as you would expect, bits, checks, redundancies, and plaquettes and edges. But now a model that's been studied a lot in fractons is this 2D plaquette Ising model. Okay, so that lives on a 2D lattice. The 2D lattice, of course, has bits, edges, and plaquettes, but by choice, you don't put the checks on the edges of this 2D model. That'll just give you the 2D Ising model, but you instead consider 4 body checks that live on plaquettes of this 2D Ising model. So now you can see that by doing this, you know, your V1 objects in your code, your checks, are no longer living on what's the V1 object, which are the edges of your manifold. Okay, you've now put your checks on these plaquettes. You've made them hyper edges because they're now acting on four bodies, 4 checks, and what this or 4 bits. And what this automatically does for you is it takes away that local redundancy that you had. Okay, if you look at this plaquette Ising model, we're now asking the question, what are products of plaquettes that you can take in order for all the bits to cancel out? And you actually need to take a product of plaquettes along an entire horizontal line or an entire vertical line in order to get a redundancy. Okay, so this plaquette Ising model has global redundancies, but no local redundancies. So if you try to do a transpose code for this plaquette Ising model, you would not get a non-trivial gauge theory. In fact, this is self-dual, and you just get back a different isomorphic 2D plaquette Ising model. To get a non-trivial gauge theory, you need to build up some redundancies, and there's a simple way of building it up. Okay, actually, for this one, it's not simple. There's a special product you can define, which we did, which takes in three Ising models. But anyway, so let me not talk about how we build it just yet. The point here is that if you now go to 3 spatial dimensions, so in principle, that should give you V0, V1, V2, and V3, okay? But now you see that you've only embedded a 2-dimensional chain complex in 3 actual spatial dimensions, okay? So if I look at a 3D plaquette Ising model, this is an Ising model, again, where every plaquette is my check. But now you can see that if you take a product of plaquettes around these 4 plaquettes around a cube, then everything cancels out and you get 1. Okay, so you had to go to this 1 extra dimension now in order to get a local redundancy. And it turns out that, you know, when we gauge these, we'll get non-trivial models. Okay, so I'll come to that in a second. So this is kind of we call this a code factory, if you will. Okay, which is like some systematic things you can do to now build these structures that you want. Okay, so in the first lecture, we already spent some time talking about how, given a particular graph, how do you define a code on that graph? Okay, so you can just put a simple Ising model on it, where the edges of the graph just agree with what you have. You can do a Tanner code, where you put the small code on all the bits that are meeting at some vertex. There's also something called a Laplacian code, which is actually like a particular type of it's not quite a Tanner code, but it's very closely related. It's, again, like a different code that you can put on a graph. And this just gives you a family of input classical codes, okay? Some of these families might have local redundancies, others may not, okay? Like the 1D Ising model does not have local redundancies, the 2D Ising model does. Once you have this, okay, so these are how I'm noting my classical codes. In general, let's stick to classical codes, which are just 1D chain complexes, the simplest ones, okay? Now you can start taking products of these classical codes, and there's various products that have been already talked about in the CS literature, and now we can unpack them in these physical terms, okay? So there's something called a check product and a cellular automata product that has been talked about, and if you look at what those are doing, they're actually creating subsystem symmetries. Okay, and those subsystem symmetries are exactly what play a big role in the study of fractal models, is the presence of those subsystem symmetries that give you restricted mobility of your excitations. And under the hood, these products are creating subsystem symmetries. Then there are other products, the simplest of which is just a tensor product. I'll tell you what that is in the next slide, I think. which create local redundancies. Okay, so this is really important. This is what we wanted, right? How do you start from codes which have no local redundancies and build a code with local redundancies, which you can then use to gauge and get a non-trivial quantum code out of it, okay? And then we defined a third product called a cubic product, which actually takes in 3 codes and produces a code both with local redundancies and subsystem symmetries. Okay, so this is actually the product that you need to get this 3D plaquette Ising model out of simple constituents, because this 3D plaquette Ising model has both local redundancies and it actually also has these kinds of, it also has these planar subsystem symmetries. Okay, so the tensor product, okay, that's the simplest thing you can do to build up a higher dimensional model from a lower dimensional one. Okay, this is basically if I told you to construct the 2D Ising model with 1D Ising models as inputs and you didn't think too hard, this is what you would do. Okay, so this is my first 1D Ising model, which I've laid out suggestively horizontally. This is my second 1D Ising model. Okay, and now you basically fill in the grid. That's the symbol for a tensor product. You fill in the grid, so you have this 2D grid of vertices, and every check that existed in each of the codes just becomes part of this new code. Okay, so by virtue of this styling, you see that you've now got a plaquette, you've created these local redundancies, and you've boosted your chain complex dimension by 1. Okay, so this is how you go from 1D Ising to 2D Ising. But actually, I could have taken a check product, which takes in 1D Ising models and returns a plaquette Ising model. So in this type of product, once again, I have 2 1D Ising models, but now the check that I built up out of them is not just, let me just take the check that existed there and there as I did for the tensor product, but you want to multiply the checks to build this bigger check there. Okay, so that gives you this plaquette, and the chain complex dimension is unchanged because, again, I'm only looking at local redundancies there. So the chain complex dimension is unchanged, but by doing this, I have created all sorts of subsystem symmetries. Yeah.
Quickly say that how the chain complex dimension changes if the 2 inputs code are different.
Oh, yeah. So if you're taking tensor products, then if you take the, I can just give you a 2D Ising model and not tell you that like it's part of a 2-dimensional chain complex. I could just hand you the bits and the checks, right? But if I specified for you a dA dimensional chain complex and a dB dimensional chain complex, and you took the tensor product and you did it correctly, then you would get a dA plus dB dimensional chain complex. But the most kind of illuminating, and indeed you can do that to build up these higher dimensional ones, but the most illuminating version of this is just 1D chain complexes, which cannot be gauged to give you something non-trivial, and you combine 2 of them, and then you get a 2D chain complex. Yeah. But this one doesn't change. This one, if I gave you dA and dB, maybe, which, yes, this one, I want to think of it just with 1 and 1, and then I'll be left with something which is 1-dimensional. Or yeah, so I haven't thought through exactly what this is if one of those already had local redundancy. The local redundancies just won't change, basically. Those will still continue. Yeah. Yeah.
Sorry, just clarifying the previous slide. What do you mean? I'm not sure I quite understand what do you mean you multiply the checks to get.
Yeah, so let me do this. This is the more general one, okay? So if I have any code CA, okay, I can just, this could live on some expander graph, but I can just lay it out on some line, okay? And I'll just write the checks of it in that way. These are all going to act on like few, because the code is LDPC, they're only going to act on few bits at a time. They don't all need to be next to each other. They could be kind of spread out, but I'm just, for ease of drawing, I'm going to put it there. Okay, and then I'm going to like, so I've drawn it like that because, again, like let's just talk about the case where both input codes are 1D chain complexes. Okay, so that's why it's suggestive to draw that out in a line like that. I've drawn this out in a line like this. And now, basically, when I make this grid of bits, okay, so there's NA times NB bits, and every check that that existed in the first code, I basically, just it exists in every row of the composite code, and every check that exists in the second code exists in every column of the composite code. And now you can see that just geometrically, you're going to get checks that come together to give you these plaquettes, which are local redundancies. So this is what I mean by checks repeat, because you just take something that existed and you repeat it along every row, okay? For the check product, the language that I was using is that checks multiply, which is basically you take a check from here and a check from here, and you compose it together to make this plaquette-like check, okay? You're not just repeating it, the structure of the check is changing. And when you do this, what you can show is that in this first problem, when you compose things in that way, your logicals actually also multiply, okay? You repeated your checks, but that causes your logicals to multiply. So if you had a 1D Ising model times 1D Ising model becoming a 2D Ising model, the symmetry of the 2D Ising model is flip everybody, okay? So this is telling you, like, if you had a logical acted on by the first code and the second one, how you compose it to get a combined logical. And this tells you that for this combined classical code, the distance of this combined classical code is actually dA times dB, and the K is Ka times Kb, okay? Because you take a logical of the classical code, you take another one for B, and then you multiply them together to get a logical for the combined code. In contrast, for the check product, the logicals actually repeat, okay? So every logical that existed in your input code just gets repeated along each row of your code for CA, and everything that existed for CB gets repeated along a column for CB, okay? So you actually see that your K now is Ka times NB plus Na times Kb minus some extra redundancies that you create, which are global, okay? So these are subsystem symmetries, because now you have this bigger code combining these two sets of bits, but the symmetries of this bigger code just act on these lower dimensional planes inherited from these inputs, okay? So this is giving you exactly the type of subsystem symmetry that exists in the plaquette Ising model, but in a generalized sense, okay? And now the distance of this code is not a product of the distances, but it's actually the minimum of whatever dA or dB was going to be. Okay, and then fine, I can also do a cubic product, where basically it's like a composition of three different check products in every plane, and you can convince yourself that so this is showing you three different checks, and you can convince yourself that this creates both local redundancies, which have that kind of picture, and it gives you subsystem symmetries. Okay. Yes. So you have to then, indeed, you have to take the star products, but then you have to figure out how to glue it together properly to do this. And that gluing, I'm going to now start doing quantum. I'm going to take these classical codes with these local redundancies and gauge them to get quantum codes. And it's basically, this 3D plaquette Ising model, when I gauge it, gives me the X cube model, which is a fracton model. And there's like there's a construction for this X cube model in terms of coupled layers of toric codes. And when you're thinking in this product language, you can actually just take the analog of the toric code, which is going to be coupled layers of these kind of non-Euclidean codes, and then use those to get the non-Euclidean analog of an X cube model. Yeah.
First two products.
Yeah.
Next two product.
Check product. Yeah. Are they associative? I have to think about that. Okay. So what's this picture doing? Okay, it's actually showing you many different models, but all of which is understood in this language. Okay, so I go from 1D Ising, I take tensor product, I get 2D Ising, I gauge it, and I get the toric code. Okay, I start from 1D Ising, I take a cubic product, I get the 2D plaquette Ising model, I gauge it, and I get X cube. If I start from 1D Ising, I take the check product, I get the 2D plaquette Ising. If I gauge it, I get back the 2D plaquette Ising model, because this is just chain complex dimension 1. If I take 1D Ising and I take what's called a cellular automata product, okay, there's a cellular automata construction for this thing called the Newman-Moore model. This is a type of model where the checks live on upward-facing triangles. For those of you who are familiar with this, you know that the logicals of this basically look like Sierpinski triangles. But once again, this has no local redundancies. If you take a transpose code, you just get a dual Newman-Moore model, okay? And now you have to do some other type of special products between the cellular automata tensor product and an operation called modding to get what's called the 3D fractal Ising model. And now if you gauge that, you get Haas-cubic code, okay? And just to illustrate the point, again, this can be done for these non-Euclidean models as well. This is a Laplacian gauge theory that was actually written by Shuheng and Nathi and others here at IAS. And basically, you're starting now from one of these non-Euclidean classical codes, okay? This is just a 1D chain complex. You can prove that for the Laplacian model. It's actually self-dual. You take its transpose and you get back itself. So if you just try to gauge that, nothing special would happen. But you can now take a tensor product of this Laplacian code with just a simple 1D Ising model, okay? So that's like a coupled layer construction, if you will, but these layers are these crazy non-Euclidean graphs. And by taking this layered construction, you have a 1D chain complex, which is a 1D Ising model, and another 1D chain complex, which is this crazy geometry. And when you couple them together, you actually get a 2D chain complex. And now you can gauge that, and then that gives you this Laplacian gauge theory. So it's just reinterpreting this in this language of these products, okay? So the point is that this hypergraph product code now, okay, which is perhaps the simplest, most commonly used product construction in the coding literature, the way it's usually formulated is, here is the parity check matrix of the first code, here is the parity check matrix of the second code. This is how you combine them to get your quantum code. But in this language, all the hypergraph product code is doing is taking the tensor product of two input classical codes and gauging it. And gauging is, again, this very specific, combination of taking transposes to construct your quantum code. Okay, so I take my tensor product of two 1D Ising models. That's my 2D Ising model. And the transpose of the 2D Ising model is the CX term of my toric code. Okay, and I can take the tensor product of two dual 1D Ising models, which is also 1D Ising models, but on some dual lattice. And now when I take that tensor, I get the 2D Ising model. This tensor product gives me the 2D Ising model on the dual lattice, and transposing that gives me CC. Okay? And now the rate of the quantum code, because of this operation, is actually derived from the rates of the classical code, okay, and the transpose classical codes. And the distance of the quantum code actually also comes from the distances of the input classical codes. So for the toric code is a hypergraph product of two 1D Ising models. And you can actually see that if you go into the guts of it, almost everything that we understand about the toric code, you can trace back to some property of these underlying 1D Ising models. Okay, so the Z logicals of the toric code, which are these line-like operators, these are derived from global redundancies of the 1D Ising model. Okay, the fact that you can displace this Z logical comes from multiplying with a check of the 1D Ising model, which is an equivalence class in 1D terms. The X logicals of the toric code are derived from global symmetries of the 1D Ising model. So between the symmetries and the redundancies of those input 1D Ising models, you get the X and Z logicals of your quantum code. And because the input codes were just one-dimensional, and your logicals are coming directly from those, you know that your distance cannot be greater than root n when you take this kind of hypergraph product, okay? Because everything here is just being derived from the input that was coming in. And notice also that in the toric code, we know that point-like excitations, the excitations are point-like, and they're deconfined. And actually, this is, again, derived from the domain walls of these input 1D Ising models. Okay, in your input 1D Ising model, you had a point, you have point-like excitations which are domain walls, and once you've created domain walls, you can actually move them around at no cost, and that's exactly the same property that the charge and vortex excitations of this toric code have, and that again comes from these 1D Ising models that it's derived from. Okay, so I like this a lot because it means that, like, you know, you can invest a lot of effort in just understanding the stat mech of those classical codes, and then when you put them together to construct quantum codes out of it, you can predict what many of the properties of those quantum codes are going to be. Okay, what the excitations would look like, what their mobility would look like. So this thing that I alluded to, which I won't get to talk about, you know, in thinking about these input classical LDPC codes as spin glasses, that has an interesting kind of prediction for, you know, what you get when you build a quantum code out of those inputs, because, you know, those are spin glasses, the excitations in those are very restricted, you know, they can't really move about very much. So from that point of view, it looks very confined, but then there's also a sense in which, you know, it's giving you something which is locally indistinguishable and has topological order. So it's kind of some weird mixture between, you know, you usually think of the toric code as a spin liquid, but then this model gives you a type of spin glass. So, you know, I don't even kind of know what to call that yet. But the point is that, you know, because these products take in those classical inputs and then build up higher, you know, souped up versions, you can get very far by just understanding what those classical inputs are. Yeah.
In a higher dimensional code, is there a way to decompose it into a product of lower dimensional code?
So again, the thing that's relevant is the dimension of the chain complex. So even though the code lives in infinite dimensions, okay, with this kind of with this Euclidean, with this non-Euclidean lattice, if there are no local redundancies, which again in some of the models that I was mentioning with high probability that's true, okay, then it's still a one-dimensional chain complex, even though it's living in some crazy large dimension. But that means you don't need to decompose it any further. In terms of chain complexes, it's as decomposed as you want. Okay, I mean you can, because it has subset symmetries and so on. But okay, but you know, at least from this purpose, you don't need to decompose it any further. Okay, so this is just several of you were asking me yesterday, like, what can you have higher dimensional chain complexes? And certainly, you know, you just have these larger boundary maps. And now, you know, for just like I could embed a classical code into a quantum code, and that told me about the redundancies of the classical code. Now I can embed, if I have this 4D chain complex, I can take these middle 3 levels. I can actually not, you know, I have a choice on where to put them. But if I take these middle 3 levels and associate it with qubits, z checks, and x checks, then the presence of these extra levels here will give me local redundancies on the z checks and local redundancies on the x checks, again, from the structure of these maps. And because these have local redundancies, you know their excitations are going to be loop-like. And that's exactly what gives you thermal stability for the 4D toric code. Okay, but if you just had a 3D toric code, then you can make one of those excitations loop-like, but not the other, and then you don't get the thermal stability. Okay, good. So, all right, so almost done. Okay, so where we are now is that, you know, what I've shown you is that if you start with this 1D model with these parameters, which is very, you know, k not scaling with n, d equal to n, and I go to this non-Euclidean expander graph, I can get a good classical code. Okay, so from the classical point of view, I'm basically done at that point. Now for the quantum case, I go from this 2D Ising model, okay, which when I gauge, I get the toric code, and the toric code actually saturates the Bravi-Pull inter-Hull bound, but notice that it's got very poor parameters, right? Like k is just 2, so I have to pay a huge overhead in trying to build a quantum computer, because I have to pack in lots and lots and lots of physical bits to get a good kind of robustness with this distance, which is only going as root n, but then I only get 2 logical bits out of that, right? But then if I just take a product, a simple tensor product of these 2 kind of 1D chain complexes corresponding to these codes, and I gauge it, so this is the hypergraph product of some code like the ones I talked about on the first 2 lectures, this already gives you a huge improvement, okay? It doesn't get you all the way to a good code, but this is already pretty darn good, right? Like, because you see that, you know, your K is now proportional to N, which is coming from this input there. But D, when you take this hypergraph product, because the properties of the quantum code are coming from each input individually, and by the time you take the product, each input individually is only involving square root of N of the bits. This D cannot be greater than square root of N when you're taking a hypergraph product, okay? So this hypergraph product was, I think, developed about 10 years ago, still quite a few years after the good classical LDPC codes. But the big challenge in going from this hypergraph product to good LDPC codes was in how to boost this square root of N up to N, okay? And basically, you have to now get into, you have to now kind of dress this product in some ways. So there was a paper by Hastings, Ha, and O'Donnell that basically first surpassed the square root of N barrier, and they took they constructed a special type of manifold where I think this could go to, I forget exactly what the power was, maybe 2/3. Don't quote me on that. But then, you know, very soon after that work, which first broke that barrier, it was developed how to take this kind of balanced or lifted product where you basically have to have input codes which have some enhanced symmetry, okay? And then you take this product and then you mod out that symmetry, and by modding out that symmetry, you can boost this distance, okay? So that's what this is showing here, okay, where I had my hypergraph product code, and then I have to do one extra step in it, which is to mod out the symmetry and then gauge it, and then I get this good quantum code, okay? So what does this mean? The point is that, you know, when you've taken this hypergraph product, you've gone from some 1D systems in real space to 2D, right? You've multiplied your number of bits. But if your model had a lot of symmetry, if you now take that symmetry to mod the system down, okay, then the way you're boosting the relative distance is not by pushing the distance up, but by doing this modding in a way that your logical remains unchanged, but the number of effective bits is shrinking, okay? So you boost the relative distance d over n, but actually by reducing n. And the way you get these symmetries G, again, ties back to something we learned about yesterday, which is you take very symmetric input classical codes, which are built out of these Cayley graphs. Okay, so you start with these very symmetric graphs. You can put codes on them, which also have some properties and symmetries. And then that gives you some very symmetry-enriched structure here. And then by modding that out, you can get this type of good code. Okay, so it's just a very, very simple cartoon figure for what this would look like for, again, just some 1D models where, you know, suppose you had translation symmetry by 2 lattice sites and 1 lattice site. Okay, so you now built up a tensor product there. But then everything that you can get to by the combined action of those 2 sites, so, you know, in this case, I go 2 left and 1 down, should all be identified. Okay, so all your diagonals get identified, and you basically go from this 2D system to this effectively 1D system with these longer range interactions. And that's this modding out of the symmetry, which has shrunk your lattice down. Okay, so we actually just played this game, you know, not trying to build good codes, but we just took Newman-Moore models and Ising models and constructed higher dimensional things, and then kind of did some modding out. And what we ended up getting were actually like some cute examples of symmetry-enriched topological order. And for a couple of days, we were happy thinking we'd found something new, but then we found Xiaogang's papers on it. But okay. All right. So these balanced product codes finally achieved this holy grail of constructing this good quantum LDPC code. And the same construction was actually also used to construct these good locally testable classical codes. I won't tell you what they are. They're just some codes which have a particular structure in their energy barriers that make them very, very useful. And now that we understand things from the point of view of gauging, what we could show is that in every known example of a good quantum LDPC code, it's actually gauge dual to a locally testable classical code. Okay, so these two developments that arose at the same time, they're actually related in some very intrinsic way. They're just these two models are just gauge duals of each other. And the same property that gives you this goodness in the quantum LDPC code, which is how the distance scales with n, gives you this locally testable properties for the underlying classical codes, which is about a property about energy barriers. Okay? And there's a very interesting recent paper also from a year or two ago, which showed that these good quantum LDPC codes obey something called the NLTS property, which is no low temperature trivial states. And this is actually like a very strong form of topological order from the point of view of physics, because what it's telling you is that if you define trivial or non-trivial states based on the depth of some circuit that you need to prepare it, then in these classes of codes, if you're below some temperature Tc, it doesn't have to be an eigenstate. Any state that exists below that Tc cannot be prepared by a finite depth circuit. Okay, so notice that this is very different from the toric code, right? Because with the toric code, if you want to prepare the ground states, you can't do, let's do 4D toric code, which also has a Tc, right? 4D toric code is thermally stable, but it doesn't have this NLTS property. Why? Because you can, if you want to prepare a symmetric kind of eigenstate of it, then indeed you'll need some large depth circuit. But if you just want to prepare any state below Tc, well, then you do the kind of tiling argument that we went through in the first class. You just tile your system into finite chunks, and you put a toric code state below some temperature in each of those chunks. Because the chunks are finite, you can prepare those states with a finite depth circuit. But now the energy penalty that you pay just scales with the boundaries between all those chunks. And by tuning the relative size, you can take that surface to volume ratio to 0, and you can make a state as low temperature as you want, but which is also trivially preparable. Okay? In these expander codes, precisely because the bulk and boundary scale proportionally to each other, this type of construction is not possible. So you end up getting this very kind of robust type of property. And it also points to, this interesting question of like, what else in when we're thinking about spin glasses, again, because you have this bulk and boundary scaling similarly, many things which are very hard to prove and debated about very ferociously for finite dimensional spin glasses now just kind of follow very, very directly and naturally in these kind of expander code models. Okay, so when bulks and boundaries scale similarly, StatMech can change in interesting ways is the message. Okay, so so this is basically like a web of dualities that we just parse through, where you can take like a whole zoo of interesting models that people have studied. I told you some of these models, but you have various other fracton models studied here, like X cube and Yoshida's fractal liquid. You have different types of SPTs. This is the Rausendorf, Brown, and this is the Harrington SPT. This is a different kind of SPT. These are protected by different types of symmetries. And what this picture is showing you is that by taking these ingredients of check product, tensor product, gauging, and there's actually another operation which I didn't tell you about, which is Higgsing. Okay, you can, once you have this Tanner graph, you can actually put a cluster state on that graph that gives you an SPT. And it's exactly the SPT that you would have to measure to get the non-trivial kind of quantum code out of it. So just by following these simple operations, you can get this whole zoo of different models, okay? And you can uncover these relationships between them that people have studied. And by organizing the products in this way, you can organize this zoo in terms of increasing chain complex dimension, okay? So these are all models with just chain complex dimension 1, so there's no non-trivial gauge theories. By the time you get to chain complex dimension 2, you can have some non-trivial CSS codes, which are these teal boxes. By the time you get to chain complex dimension 3, you can get even more of these gauge theories, but you can also get kind of SPTs, which are very, very robust because you can get the extra layers in the chain complex basically promote zero form symmetries to one form symmetries because they give you these local constraints and these local relations. So by going down this path, you can get more and more kind of souped up models. And now the interesting thing is that the only feature that all of these things, all of these products need about the 1D Ising model is that it's a one-dimensional chain complex. Okay, so I can now take that root there and replace it with an expander graph with no local redundancies like the types we have looked at already. And now you can just follow this through and build kind of non-Euclidean analogs of all of these phases. Okay, and I don't know, there might be interesting things there, right? Like, but it's just, it's a very kind of constructive way of following that through. So, this is just like what you could do if you wanted to run this code factory, pick a graph, pick a model on it. You can take check products, get another 1D chain complex souped up with some subsystem symmetries, take some other model, and then you can take a tensor product. You can mod out some symmetries, you can gauge it, you can Higgs it. Okay, so you can just play this game now with your favorite models, and they don't even have to be non-Euclidean models, right? Even for Euclidean models, the structure might help you come up with some interesting new cases. So, okay, so that's my last slide. The key messages are that these LDPC codes furnish an interesting new class of StatMech models for many body physics. They lead to novel new phenomena and non-Euclidean geometries. We can understand these quantum LDPC codes as generalized gauge theories with these generalized Kramers-Wannier dualities. Actually, there's also generalized Kennedy-Takasi dualities when you're thinking about the SPT versions of them. And you can unpack different product constructions in the coding literature in these physical terms. And the unified description of all of this is via homology. Okay, so other results that I didn't talk about, but I just very briefly mentioned right now, is that you can use these chain complexes to define SPTs. And you can study the dynamics and thermodynamics of these codes. That's the paper that we're writing up right now. And the thermodynamics and dynamics also ends up being very interesting. You end up getting these classes of spin glasses. And I'll end with saying like a major open question in the study of LDPC codes is how to do logical gates on these. Okay, so everything I've told you about right now is how do you encode a large density of logical information. Okay, but once you have a large density of logical information, you actually don't want it to just sit there. You want to start doing ideally a universal gate set on those logical qubits. But the same features that make them good codes also make them very hard to operate on. Okay, so there's a lot of people who are actively thinking about how to do gates on these models. And a hope could be that maybe thinking also along these physical lines, because there are other works, notably by Yoshida early on, in trying to use this kind of gauge theory prescription to do gates on kind of conventional codes. So maybe this way of thinking about it could also help us solve that problem. Okay.
Questions?
Comment on generalization to include non-abelian particle order.
Yeah, that would be very interesting to do. I think you'd want to first start by thinking, again, in the language of these chain complexes. Even just doing U1 and Zn to start could be quite nice, actually. U1, I think, could be very doable. So that's where I would start, and then maybe move on to non-abelian. Yeah.
Yes. So it looks to me that this whole procedure for the past 3 lectures like we have gone through, if my quantum code is made of qubits, so long as it's prime power dimension. So is there anything you expect to be interesting in here, or spin half is basically all that?
Is there something interesting if you increase the dimensionality of the qubits?
Yeah, or at least for the odd prime powers where we know the stabilizer formality still goes through.
Yeah, potentially, I don't know. Yeah.
So if I understand correctly, all these models are done in a Hamiltonian on a lattice.
Yes,
It might not be periodic and continuous time.
that's right.
How much of that can be done on a discrete Euclidean space-time?
Good, yeah.
Classical statistical mechanics.
E-
The time doesn't even have to, Euclidean time doesn't even have to be periodic.
That's right.
Just in case, for the story code, I know it's the same thing.
Exactly, and that's the, so you'll end up getting, so those gauge theories come up. There's various things I'm trying to disentangle. So one is, when you have this type of perspective and you try to do error correction on these codes, actually there's a description for error correction in terms of StatMech mappings. And the StatMech model that you get like for the toric code to decode it, you get a disordered version of a 2D Ising model. If you don't have measurement errors. If you have measurement errors, then you get an extra third dimension, and that very much is like Euclidean time. So if you want to start decoding these models and thinking about very generally trying to do that and trying to come up with the StatMech model that you would need to decode it, they would have exactly the type of structure. So we just put out a paper where some of this is alluded to. It would have exactly the structure that you're mentioning, where there would be like a third dimension where it's basically the code, but that third axis just looks Ising-like. It's not souped up in any way. So that's one comment. And then another is also, people have also started thinking about space-time codes, where it's not just information that's encoded in space, but this is not real, like actual time. Like there's some dynamical process that encodes and operates on that information. It would also be interesting to think of that in this language. Now time is entering in in a real way there, and how to, maybe someone already knows how to do this. I don't, but like how to put, how to think of those types of codes in this language is another thing. Yeah. Yeah.
Operation that you have here, clear counterpart.
Right.
In the other picture. So is it
Exactly.
easier or harder? Does it give you new relations or not?
Yeah, so at least we did find it useful to think in terms of that classical model for, well, the question we were trying to answer is, there's various results on stability that are known for local Euclidean models, right? Like they're like these papers by Hastings, for instance, where you can, where these conditions that give you topological order are also the conditions that give you some kind of error correction, and those are also the conditions you use to prove phase stability. Now, there's various, for these models, you can have thresholds for their error correction properties, and those are known to exist at very minimal assumptions, including on these lattices. But results for stability of phases, I showed you the zero correlation and fixed point, that doesn't really exist beyond Euclidean local models. So what we were trying to do is to say, like, if I know I have a threshold for error correction, that defines for me a classical StatMech model exactly of the type that you're saying. Can I use some properties of that model to then argue for stability of the corresponding kind of quantum model? So we didn't solve the question fully, but we took some first few steps in that direction. Yeah, and their thinking about that classical model did help us a lot, actually. Yeah.
All right, well, let's thank Vedika again, and